Hi, I'm Ravi, and I'll be talking about safe and efficient exploration of human models during human-robot interaction. As robots continue to become more common in both household and manufacturing settings, they need to stay safe around people, especially since many collaborative tasks require the robot to be in close proximity to humans. In this work, we consider a single human and single robot interacting, where the human and robot can observe each other's state. The robot's controller contains a model of the human that gets updated online with new observations. This model and the robot's state are fed into the robot's control policy, which is used as the reference control for a safety controller that outputs the actual action of the robot. Importantly, the robot can only stay safe around human with respect to its own model of the human's future behavior. So in this paper, we pose the question, how can we improve the robot's model of the human during the interaction? Before tackling this question, let's briefly discuss how our robot stays safe with respect to the human. If we consider a single integrator robot system, the control inputs are its x and y velocities. If we want to keep the robot out of the red region, the set of safe controls that keeps the robot outside this bubble is defined by this shaded half space. The safe controller takes some reference control in this space and projects it to the closest vector in the safe set. Additionally, if the robot is uncertain about the human state, the unsafe region will enlarge, which in turn shrinks our set of safe controls. To reduce this uncertainty, we investigate different active exploration strategies for human model learning in an interactive scenario. As a running example, we consider a 2D simulation of a collaborative manufacturing task where the human is in blue, their goal state is in green, and the robot is in red. When formulating active exploration in this scenario, we can consider different optimization problems formed by different risk preferences, where risk refers to the chance of incorrectly predicting the human state. The results are shown here to give an intuition for what each risk preference means. As a baseline, we consider a risk-neutral or passive robot that doesn't account for uncertainty. We also consider a risk-averse controller that tries to minimize the future uncertainty in its human model. And finally, a risk-seeking controller that tries to maximize the model uncertainty in hopes of getting observations in high uncertainty states. We're also interested in understanding how these risk preferences are affected by the specific kind of uncertainty the robot has in its model. If it estimates the portion of the human's dynamics that only depends on the human's previous state, then we'll say the robot has intrinsic uncertainty. If it estimates the portion that depends on the robot's previous state, then we'll say this robot has interactive uncertainty. And finally, if the robot is estimating both, then it has full uncertainty. We explore how the robot learns under each of these three conditions for each of our three risk preferences, giving us these 9 different scenarios. As an instantiation of this problem, we consider the case where the robot is estimating a linear system of the human's dynamics. So the robot has intrinsic uncertainty in the A matrix and interactive uncertainty in the B matrix. We'll introduce a particular form of UH later, but it generally captures external stimuli for the human. The robot is trying to estimate the dynamics of a simulated human online. The simulated human's control takes inspiration from the social force model of humans, where the human is attracted to its goal and repelled from the robot, where gamma controls how strongly it's repelled. Concretely, this means the human would move like this towards its goal if the robot was stationary. To evaluate our simulations, we measure the one-step prediction error of our model as it adapts online during the interaction, and check how well the model generalizes by computing the held-out error as the average one-step prediction error on a held-out set of trajectories with different initial conditions. The x-axis here denotes time, and each curve is averaged over multiple initial conditions. Note that these controllers were run without the safety controller first so we can get a baseline understanding. When the robot has only intrinsic uncertainty in the human's dynamics, all 3 risk preference controllers have the same performance on these metrics. This seems to make sense since the human model in this case is not a function of the robot's state, so changing the robot's control won't change how the model learns. When the robot keeps only interactive uncertainty, we see a stark difference between the controllers. The risk-seeking controller learns the best overall model of the human, while the risk-averse controller is able to keep the one-step prediction error very low. This is essentially because the risk-seeking controller gets better interactive data to learn from, while the risk-averse controller steers the robot away from interacting with the human at all. Finally, when the robot has full uncertainty, the differences between the controllers are less pronounced because the robot starts with a higher model error. Finally, we introduce the safety controller back in and plot the performance in each scenario in the dotted lines. Importantly, the performance for all the controllers is essentially the same before and after the safety controller is introduced, except in one case that I'd like to zoom in on. When the robot uses a risk-seeking controller, the held-out error doesn't decrease as much when the safety controller is active, as we can see from the difference between the normal and dotted lines. To get a better understanding of why this happens, let's look at one example trajectory from this scenario when the robot has interactive uncertainty. The risk-seeking controller tries to keep the robot close to the human, but it importantly breaks the minimum safe distance from the human. So when the safety controller is active, it changes the human and robot's trajectories a lot. This means we have a trade-off between improving the human model and keeping the human safe. The risk-averse controller, though, just decides to run away from the human so it has the least influence on them, so the safe controller won't change anything. Finally, the risk-neutral controller only occasionally gets close enough to the human to activate the safe controller, so its trajectory also doesn't change significantly. To dive deeper, we look at what happens when we change the amount of influence the robot has on the human. This is what the human's control would look like using different values of gamma, which is our hyperparameter that controls the influence of the robot on the human. We can again look at the held out error and see that the gap between the safe and unsafe risk-seeking controllers actually closes when the influence is high, meaning that the robot could significantly improve its model of the human using this controller while still staying safe. This work tells us that active exploration is beneficial when the robot has interactive uncertainty, less information is gathered using risk-seeking control if the human is reckless around the robot, and that adaptation will improve both immediate error and model accuracy, regardless of the risk preference, to enable safe and efficient collaborations like we see here. Thank you.